Okay, so we're in section 2.2 now, and we're talking about the limit of a function. Now, section 2.1, we addressed what we were calling the tangent line problem. And the tangent line problem is really what motivates the concept of a limit, which is what we're talking about here. And then as we're going to see as we kind of move through the course, pretty much all of calculus comes from this idea of a limit. So just to kind of recap on what we did before, when we were looking at trying to find the equation of a tangent line, the most important part of that for us was trying to determine what the slope of that tangent line was. And the idea was that we took a curve, we found a point that we wanted to find that tangent line at, and then we picked another point. First point we were calling P, a second point we're going to call Q. We brought that point Q closer and closer to the point P, drawing secant lines through those 2 points every time, and then use that as an approximation to our tangent line. That idea of approaching, bringing that point Q closer and closer to that point P underlies the idea of a limit. Okay, so before we get into a definition of the limit, I want to talk about something that we call a limiting process, because this is actually a very useful concept in the kind of applications that calculus appears in. So what is a limiting process? I like to think of it as kind of a two-step thing. The first step is you're deriving some function that we're going to call f of x for this discussion here. And that function provides approximate solutions to some problem that you're trying to solve for given values of x. And the idea here, which the rest of this paragraph kind of outlines, is that as x is brought closer and closer to some specific number a, the function f of x gives better and better approximations to whatever the actual solution of our problem was. Now that was what we saw in section 2.1. If you remember, we came up with a function that determined the slope of a given tangent line, or secant line rather, for different choices of this point Q. We used, in that case, the x was the x coordinate of that point Q, and we found that as we brought x closer and closer to the input that we were interested in using for our tangent line, our slopes got better and better at approximating the true slope of that tangent line. We couldn't plug in the x coordinate for the point P, because in that case the function ended up looking like 0 divided by 0. So instead of plugging in the number directly, we had to approach that number, and that's the idea behind a limiting process. So in 2.1, this function f of x would have been that slope function, the function that gives us the slope of different secant lines. Okay. Now, the second part of this two-step process is, again, evaluating f of x using values of x that approach that value of a until the approximations begin to suggest a true solution to our problem. This is going to sound really vague at this point. Really, the only application that we've seen of this idea was that tangent line problem. But we're going to use chapter 2 to kind of build on this and get some practice working with this idea. But before we do that, I'm going to give the intuitive definition of a limit and introduce some notation. So let's suppose that we have some function f of x, and let's suppose also that f of x is defined when x is near a specific constant, a specific number a. And really what this means, you see in the parentheses here, it means that f is defined for all of the values within some open interval containing a, not with the possible exception of the point a itself. Okay? Then we write this. We say the limit as x approaches a of f of x equals L. That's how we read this. The limit as x approach, or the limit of f of x as x approaches a equals L. Okay, and we say that if the function f of x can be brought arbitrarily close to L, which means as close to L as we would like to make it, by restricting x to values that are sufficiently close to a on either side of a. And again, this is going to sound very vague what I'm talking about, because we haven't really done examples yet, but we're going to make this more concrete as we move along. So This notation is also used fairly frequently. So we don't use the LIM here, but this means the same thing. F of x approaches L as x approaches A. That little arrow, we read that like the word approaches. Okay? Now in this section, we're going to be looking at evaluating limits using two different methods. Neither of which are going to be the method that we end up using the most. 2.3, we're going to talk about the algebraic method for evaluating limits, and that's the one that we're going to be using the most. But as we're still warming up to the idea of a limit, the two approaches that are the most accessible right now are going to be the graphical approach and the numerical approach, which we'll talk about down in the second example. So for this first example, notice the use of this symbol that we've defined. It says we want to determine the following limit graphically. The limit of the function x minus 3 over x squared minus 2x minus 3 as x approaches 3. Okay, now it's tempting to want to say, well, why don't I just plug the 3 into this function, and that should just tell me what the limit is. And in certain cases that actually does work. We'll talk about exactly when that works in a later section. It will not work here. Think about what happens if you try to plug 3 into this function. 3 minus 3 is 0. Down here I get 3 squared, which is 9. Minus 2 times 3, that's 6. So 9 minus 6 is 3. Minus 3 is 0. This works out to 0 over 0, which is undefined. This function is not defined at 3, but it is defined everywhere else, at least everywhere else near 3. It has another discontinuity, but it's nowhere near 3, so that's not important. If we were to graph this function, say in a graphing utility, like a graphing calculator or Desmos or something like that, you would get a curve that resembles well, this is a rational function, so this is part of what that curve would look like. And again, we're approaching 3 with our x values. So as x gets close to 3 from this direction or from this direction, what's happening to our y values? Well, as x approaches 3 this direction, if you follow the points on that curve, all of the y values are right above 0.25, but are getting closer and closer to 0.25 as we approach this little hole right here. If we approach x from this side, from the right side, so our x values are slightly larger than 3, but approaching 3, then if we follow the points that we would be graphing on that curve, the y value of these points are approaching 0.25 from down below. So even though this graph doesn't have a point here, that hole indicates that the function is not defined there. We can still see that it is approaching a specific number. The outputs of that function are approaching 0.25 as our x values approach 3. And so that is what I would call my limit. The limit of x minus 3 over x squared minus 2x minus 3 as x approaches 3 is equal to 0.25. That would be the limit in this case. Okay, so the graph kind of points us in the direction of that limit if we know how to follow that curve. Here's another example. We could do this using the graphical approach as well, but we're going to try a different method for this. This one says that we are to guess the value of this limit below by using a table of values. Now, this is the limit of the function f of t minus 1. Oh, sorry, I don't know why I said f of t. 5 to the power of t minus 1 over t as t approaches 0. And once again, you might be tempted to say, you know, why do I have to deal with a big table of values? Can't I just plug in 0? But again, look at what happens when you try to plug 0 directly into this function. 5 to the power of 0 is 1. 1 minus 1 is 0. Plugging in 0 down here gives me a 0 in my denominator, and 0 over 0 is undefined. Notice the same thing happened up here when we try to plug that number in directly, 0 over 0. Even though plugging it in directly gives us something that's undefined, the limit still exists and gives us a specific number. Okay, so we might expect the same thing to happen here. And again, this function, right now I'm not attaching any context to it. I'm not showing any application that uses this function, but it could very well be that this function represents the slope of a tangent line to some specific curve. So we've already seen that this might come from somewhere useful. Okay, so how do we do this numerical approach? Well, the idea with the numerical approach is to create a table of values, and we did this in the last section. So this should feel familiar. I'm going to have t, and then I'm going to have my function 5 to the power of t minus 1 over t, and I'm going to create a table. And the idea here is I want my t values, I want my t's to approach 0, but I want to approach 0 from both sides. So, for example, I could approach 0 using positive numbers. Say I start with 1. Then maybe I could plug in 0.1. That's a little closer to 0. Maybe 0.01 next. That's even closer to 0. 0.001. That's even closer to 0. So these numbers are approaching 0 from the positive side as I move down this list. Okay, but I want to see what happens if I approach 0 from the negative side as well. I want to see both sides of this thing. So a number that's really close to 0 would be negative 0.001, so basically just the opposite of this. And then I could kind of create a mirror image of sorts, do the negatives of all of these, so negative 0.01, negative 0.1, negative 1. Okay, now I would use a calculator to get all of these outputs. You can easily find the outputs by plugging in a 1 or a negative 1, just by hand, but these other values are going to be a little complicated. So if I were to use a calculator, these are the values that I would end up getting. 4, 1.622, and I am rounding most of these, so it's not exactly 1.622, it's rounded. 1.622 again. These two numbers would actually be different, but they round to the same thing. 1.611, 1.608, 1.597, 1.487, and this one comes out exactly to 0.8. Okay, so that's a lot of data that I've just collected, but where in this table am I going to find an answer to the question that I'm trying to answer? Well, again, we're looking for the limit of this function as t approaches 0. And t is approaching 0 from the positive side here and from the negative side here. T equals 0 is going to be somewhere in between negative 0.001 and positive 0.001. So I'm expecting my limit to be somewhere in between these two outputs, 1.611, 1.608. Okay? Now, exactly what my limit is equal to, I don't really have enough information to find that right now. We will be able to answer that question later when we develop better methods for doing these limits, but for now, the best I can do is make an educated guess. And that's why it says guess the value instead of find the value. So what's a good guess if I know my limit's going to be in between these two numbers? Well, one way to find something in between these two numbers is to take their average, to take the mean of these two numbers. So I think a good way of evaluating this limit, the limit as t approaches 0, of 5 to the t minus 1 over t, based on what I'm seeing in this numerical data here, I would expect this to be approximately equal to the mean of these two numbers, 1.611 plus 1.608 divided by 2. That's how we average two numbers. And this comes out to 1.66095. Is that the exact limit? No, it's not. But based on the data that we have, I would expect that to be very, very close to the actual limit. So it serves well as an approximation. Okay, let's go ahead and move on. Now, there are a whole lot of different instances where a function may fail to have a limit. There's a very classic example in something that we call the Heaviside function. This is named after a person, that's why it's capitalized. We can define the Heaviside function as a piecewise function. It's always equal to a constant, but the constant varies depending on where your input lives. So the Heaviside function, h of t, capital H of t, is equal to 0 whenever our input t is a negative number. It's equal to 1 whenever t is a non-negative number. 0 or positive is what that would mean. And this is just a definition. This is how we define this function. This function shows up in a lot of applications. It shows up in signal processing, electrical engineering a whole lot. This oftentimes represents, t represents time, and our vertical axis represents a state of a switch. So 0 might represent off, 1 might represent on, and as time passes we switch that switch on right here, so it goes from 0 to 1. The applications of this are not important for this discussion, but this does show up in other places. So if I wanted to try and evaluate a limit of this function, in particular if I wanted to find the limit of h of t as t approached 0, because I have a graph to look at, I would try the graphical approach. But the graphical approach reveals that there's not going to be an answer to this question. And the reason for that is if I approach from this direction, meaning if I were to take values of t and keep plugging them into h of t, bringing those values of t closer and closer to 0, but from the negative side, then it really doesn't matter how close I get to 0. As long as that value of t is negative, h of t on this side is going to always equal 0. If I do the same thing but use positive numbers that are getting closer and closer to 0 but from this side, then no matter what, as long as that number t that I'm using for t is positive, by the definition of this function, h of t is always going to equal 1. It never really changes until we move into the negative numbers. So the limit, depending on which side we're approaching from, is giving us different values. And what that tells me is that the limit doesn't exist. Compare that to what we saw back in this graphical example here. As I approached 3 from either direction, the curve was going to the same point, from this direction as well as from this direction. It was zeroing in on that 0.25 right there. However, looking at this graph, as we approach 0 from the left, or as we approach 0 from the right, we're going to 2 different places. So in that case, I would say that the limit of h of t as t approaches 0 does not exist. That's one way that a limit can fail to exist. Now, even though the limit doesn't exist here, we can kind of we can kind of change up our definition, get a definition for a different type of limit that might actually apply here. And this is where we get into what we call one-sided limits. So again, looking at this definition, or this example up here, as we approached 0, as t approached 0 from the left side, meaning from using values that are to the left of 0, these negatives over here, then the limit appeared to be approaching 0. As we approached from the right, as t took on values that were closer to 0 but still to the right of 0, meaning in the positives, our function appeared to be approaching 1. So in this case, even though the limit itself doesn't exist, I do see numbers that this appears to be approaching from the left or from the right. And this is where we get these things called one-sided limits. So here's the notation that we use for that. I say that the limit of f of x as x approaches a from the left. Now you see that little negative sign up there. It's not actually making a negative, it's appearing in sort of an exponent. And we read that as from the left. What it means is that we're approaching x using values that are getting close to a but are always smaller than a. We call this a left-hand limit if it exists. Okay, and then similarly, a right-hand limit looks like this. This is the right-hand limit of f of x as x approaches a. And in this case, we're saying it equals L if it exists and it's approaching that number L. We also can say that we're approaching a from the right. What that means is that we're evaluating this limit by only plugging in numbers that are getting closer and closer to a while always remaining to the right of a, meaning they're always larger than a. Okay? And so this example up here of the Heaviside function, we see a left-hand limit and a right-hand limit. And down here is how we extract some information based on what we just saw up there. The left-hand limit of h of t as t approaches 0 is equal to 0. And the right-hand limit would be equal to, that should be a 1, that's a typo right there. It's equal to 1. And that's what we were seeing up here, okay? So left and right-hand limits. Now, this leads to something that we would call a theorem. I'm not going to be too picky about the language there, but this is where we establish the connection between what we're just calling a limit and what we're calling left and right hand limits. And basically what it says is that the limit of a function f of x as x approaches a is equal to L if and only if, that has specific meaning in math, if and only if the function has the exact same left and right hand limits at that number a. So again, this means as we approach a from the left, the limit is L. As we approach a from the right, the limit is the same L. Okay, so this is one way of determining whether a limit exists or not and what it would be equal to. All right, so let's take a look at another example, and we want to do the graphical approach here. In this example, we're given a graph. We're not given an algebraic representation of this function. We're just told that it's y equals f of x, and this is part of its graph right here. And we want to look at a few different possible limits here, whether just regular limits, which we also call two-sided limits, or one-sided limits, or even a couple of examples of evaluating a function explicitly with no limit involved whatsoever. So let's take a look at this first one. I'd like to find the limit of f of x as x approaches 4. And x is what's approaching 4. I look to my x-axis here and I find 4, which is here. I want to approach 4 from both directions because we're looking at a two-sided limit. I know that because this 4 doesn't have a plus or a minus appearing in the form of a superscript, like an exponent. What appears to be happening as we approach from the left? Well, as we approach from the left, if I follow this curve, as we approach from the left, we appear to be approaching 4, but from down below. These points would have y values that are just below 4, but getting closer and closer as x approaches 4. As we approach 4 from the right side, then I'm looking at points on this curve that are getting close to this hole right here, but they're also approaching from down below. And it doesn't matter if they're approaching from below or above. What matters is that on both sides, the function is approaching this point. The curve is approaching this point, which has an output or a y value of 4. So I would say that this limit is equal to 4. Okay? The fact that these are both 4s is coincidence. That 4 is on the x-axis. That 4 is on the y-axis. Okay? So that's one down. F of 4. What is f of 4? Well, this is different from the limit as x approaches 4. This is saying that we plug 4 directly into our function. And in order for me to find f of 4, I would have to find a point that appears on this graph with an x-coordinate of 4. But no such point exists. I have a hole in the only place where it looks like a point might have existed. So this doesn't exist. This function is undefined at x equals 4, at least as far as we can see from the part of the graph we're given here. Okay? Let's try a different question. The limit as x approaches 2 from the left-hand side. So we're looking at the limit of f of x as the left-hand limit of f of x as x approaches 2. That means I only want to look at x values that are on this side of 2. And those points, the points on the curve corresponding to those values that approach 2 from the left, all appear on this little branch of our curve. And you can see that they're approaching this solid point right here. What would the output, or what would the y-coordinate of that point be? Well, it's right between 2 and 4. It looks like that would be 3. So I would say that that left-hand limit is equal to 3. Okay? The next part asks me to find a right-hand limit. That's what the plus indicates. So it's still approaching 2. X is still approaching 2, but now from the right. We're now looking at this direction. And if we're to the right of 2, all of the x-coordinates that have values that are close to 2 but still to the right of 2 exist on this part of our curve. So I'm approaching from this direction now. And that appears to be approaching this hole. The function the curve doesn't have a point there, but these points are at least approaching that position. And what is the y-coordinate of this hole? Well, it's 1. I can trace that to the y-axis to find that. So that would tell me that my right-hand limit is equal to 1. Okay? Now, another limit that looks similar. What is the limit of f of x as x approaches 2? Notice there's no plus or minus like there were in the previous two examples. That tells me that this is a two-sided limit. But I can tell you from this little theorem that we just mentioned right here that this limit would not exist. Okay, this thing down here is going to tell me that this doesn't exist. And why is that? If this limit did exist, if the limit as x approached, if the limit of f of x as x approached 2 was equal to some number, then that number would have to be the same thing that's appearing in my left and my right hand limits. But that would require both of these to equal the same thing. And we're getting two different numbers for our right and our left hand limits. So this does not exist. Okay? Still working with the input of 2, but this time we're not looking at a limit here. F of 2. What is f of 2? Well, in that case, we're not approaching 2. We're plugging it in directly. And so what I'm doing is I'm looking for a point on the curve that has an x-coordinate of 2. Looking at my 2 down here on my horizontal axis, if I sort of look for a point, I find one right here. Okay? That point has a y-coordinate of 3. So I would say that that's equal to 3. Okay? Let's try another one. What is the limit of f of x as x approaches 3? Well, 3 would be right here. And once again, if I approach 3 both from the right and from the left, we appear to be approaching that point right there. Notice there's no breaks or holes or anything of that sort at the when x is equal to 3. In a different section, we're going to define this as continuous. We would say that this function is continuous at x equals 3, simply because there is no hole or no break in the curve there. I can see that as I approach from either direction, because we're approaching this point, which has a y-coordinate of 2, that would be the limit of that function as x approaches 3. Also, f of 3, if I plug 3 directly into my function instead of just approaching it, I also get 2. Okay? Now when we have this, and again we're going to define this in a different section, but when the limit exists, the limit of a function f of x as x approaches something like 3, if we get an answer of, say, 2, if that is the same thing that we get from plugging 3 directly into our function in the first place, 2 again, that's going to be how we think of continuity. The limit equals the actual value that the function gives us. Okay, but that's kind of more of a preview of continuity, which, like I said, we'll talk about later. I'm going to stop this video here and we'll pick up where we left off in part 2.